Welcome to our August Ambassador meeting. We're very excited to welcome Dr. Alexandra Ruth Fogg, who's a space scientist from Dublin, Ireland, looking at space weather and working with citizen scientists as well. So I will turn it over to you.
Hi, yeah, thank you for having me. It's great to get the invitation. I'm going to share my screen now. So I know we have a bit of a mixed audience. So maybe for some of you, you might think I know all this already, and then some of you might be new. So I will do a little bit of background as well, but I do have some science plots. So I'm mostly going to be talking about a study we did comparing the two geomagnetic storms, the two big geomagnetic storms in 2024, so in May and October, and just relating them to sort of the science around them and how we compared them, what we compared, and what the differences we found were. So first, a bit about me. So my name is Alexandra. I live in Ireland. This is a picture of the observatory that I work at. It's called Dunsink Observatory, part of the Dublin Institute for Advanced Studies. So we are an independent research institute. We're not affiliated with a university. And you can see we have, I'm just going to turn my mouse into a laser pointer. So this main building here is built in 1785. It's a purpose-built observatory with a dome on the top. And this dome here is a bit newer, 1800 and something. Um, so some of the things we're kind of famous for, the meridian, the time, the definition of time for Dublin, when we had Dublin time, runs through the back of this building. It was about 25 minutes off London. We're now in the same time zone as London, which is convenient for me because I'm English, so all my family are in England. So we're in the same time zone now. And the other thing that we're famous for historically is the invention of quaternions, or forms of Hamiltonian mathematics. So you can just about see this equation here: I squared equals j squared equals k squared equals ijk equals -1. And that's really important for attitude directions of spacecraft and really high caliber 3D gaming simulations and things like that. And that was thought up by our third director of the observatory. He would have lived and worked in this building um, a while ago. But these days we're part of a research institute, and on this site we do a lot of space weather research. So we have two research groups: the Solar Physics and Space Weather Research Group, and the Planetary Magnetospheres Research Group. So they're all looking at the space plasma environments of the solar system, either the sun, the Earth, or the other magnetized planets like Jupiter, Saturn, and Mercury, and so on. So that's a bit of an introduction. And now to think about the science. So after the storms of 2024, which I'm sure, given the audience of this group, you are all aware of, we've already mentioned them today. We sat there and thought, well, we have our data that we've taken over Ireland. We all sat there and looked for the aurora. How can we do some science? So we took the angle of comparing the two storms. What's different about the two of them in terms of the way they were driven, and what's different about the two of them in terms of the effects that we got. And then specifically looking at Ireland and our data and observations. So there was two storms. So the one in May, often called the Gannon storm, the Great Superstorm. There are many different names for these two storms. I'm just going to call them May and October storms to differentiate them. So the May storm was the largest storm since 2003, and I have a list of some of the places the aurora was seen. So Ireland would be almost mid-latitude. That's where I live, and I saw the aurora that night as well. But there were reports like Namibia, Jamaica, all these places very close, very low latitude, which is really exciting. We also have lots of reports in the literature of issues with radio and GPS communication. There's a news report where a farmer in one of these really fancy tractors, they have them, they're really large farms in America. It's one of those automatic ones, and they just started going around in circles because the GPS was not working. Issues with satellite powered internet and, as I said, vehicle navigation, things like that. And here, this is a map from NASA. It's showing the auroral oval here over the continental North America. Here we've got Chicago. So um, then again in October we had another large geomagnetic storm. So again, aurora were visible in Ireland. I unfortunately did not see them. I think I was in bed before I got the text saying go out and have a look at the aurora. But again, we've plenty of low latitude places, and to no extent are these two lists exhaustive. They're just the ones that I have citations for right now today. But I'm sure it was seen in other places as well. And again, we saw increased drag on satellites, which is one of the risks, one of the space weather risks. So again, maybe some of you are very familiar with space weather and solar system science, but in case anybody isn't, I'll just do a little bit of a description before we go on. So this is the solar system. So I'm just moving the zoom window, sorry. Here we have Pluto right at the end. Now, when I was a child, Pluto was a planet. It's not anymore, but inside of that, we have the planets of the solar system, and the sun's atmosphere is continuously flowing out into the solar system in the form of the solar wind. And the solar wind is carrying the sun's magnetic field with it. So here we are at the Earth, we are, closer than some of the other planets, and we are really strongly affected by the solar wind and what's coming out of the sun. So space weather is an umbrella term. It captures a lot of different things, but how I'm going to use it today are the effects of the sun's magnetic field and solar wind on the planets of the solar system, but in particular on Earth. So we will say that other planets have space weather as well, but today we're just going to talk about Earth. And yeah, we are often in the field borrow terms from weather physics, so rain, wind, storms. They tend to have completely different meanings, which can be confusing if you start talking to atmospheric physicists. But yeah, space weather would be at a higher altitude than the rain that gets us wet in the day, if that makes sense. And there's only a very, very minimal effect that they have on each other. So we tend to think of them as separate for most of the time. And this is a graphic just to highlight all the many different things that space weather can affect. So space weather is a natural hazard. It's not a natural risk to us human beings when we're standing on the ground, but it is a natural hazard to our technology, which we grow increasingly dependent on. So it's something that our governments have to prepare for. And here in Ireland, I think it was 2023, that space weather appeared on our national risk assessment. And so quite recently that the government of Ireland sort of stood up and took notice of this. But in terms of, other countries, for example, in the United Kingdom, it was in a similar place in the risk matrix to global pandemic. And I think we all know that the global pandemic did in fact come to pass. So these severe space weather risks are a big danger. So we have some examples here. The aurora is the fun bit. But we also have effects on aviation industry, the drilling industry, navigation for vehicles, and things like high frequency radio communication. So there can be cases where if you have some other kind of natural disaster, you lose internet, mobile phones, and you're relying on military methods of communication like high frequency communication. If you then have a compound hazard, so space weather comes in, that can be knocked out as well. So it's very important and perhaps not as well known as some of the other hazards which have affected us perhaps for thousands of years in terms of our daily life. So moving on to thinking about the solar wind. So here we have a coronagraph. So we are looking at the sun. It's blocked, the actual sun itself is blocked out in the middle, and we're seeing the sun, and we've done that so we can see the solar wind, so the sun's atmosphere coming out the sides. And you will have some of these from the main October storms in a few slides' time. So the solar wind's very variable. Sometimes it's slow, sometimes it's fast, sometimes it's denser than other times. And when it's fast and dense, that's when it really affects us. So on average, it'll be about 400 kilometers a second. And just to put that into context, I wasn't sure whether you would be familiar with miles per hour or kilometers per hour, depending on who's in the room. So I put miles per hour. So 70 miles an hour is 0.03 kilometers a second. So much, much slower than the solar wind, is traveling really fast. And in terms of the fastest plane in the world, it's still less than a kilometer per second, compared to, so 400 times slower than the solar wind. So the solar wind's really fast, and that's the boring, or in inverted commas, boring average everyday solar wind. So coronal mass ejections then are, if I go back to the GIF here, you can see occasionally some big puffs, there we go, are coming out of the sun, and they travel through the solar system. And in this very dramatic image here, you can see how much bigger they are than the Earth. And when they come to the Earth, they impact the Earth's magnetic field and kind of wobble all the plasma inside. So the plasma is kind of like a jelly. And through a variety of different effects, they can excite the aurora, along with many other systems as well. So a coronal mass ejection will be billions of tons of material with a really high magnetic field, and it's going to take sort of half a day to a few days to get to the Earth, compared with the light from the sun, which only takes 8 minutes to get here. And this is one of the most dangerous phenomena. This is when we come to talking about really extreme space weather effects, this is the one that we like to prepare for. So here I'm looking at some stills. So again, this is a coronagraph. So we've blocked out the sun in the middle. We're looking at the outside. And something that was really special and interesting about the May 2024 storm is there were actually 5 CMEs, 5 coronal mass ejections that came out of the sun in quick succession that came and hit the Earth. So some of them, we actually showed in our paper that 2 of them, so each of these coronagraphs is showing each of the CMEs coming out. So you can see blob here coming out, a blob here. It's actually, you can almost see, sometimes the shock bubble can be more of a sphere than just coming out in one direction. CME here, here, and here. And 2 of them quite close to the sun actually crossed over and merged. And some other papers showed that as they traveled through the solar system, the 5 of them, more of them merged and became a really complex event. So this, you have the power of 5 CMEs here. And also when they cross and interact, it's not as straightforward as, 1 CME plus 1 CME equals 2 CMEs. It can be, it becomes a more complex event, and that can have a more severe effect on the Earth. So that was May. May was, the dramatic, really famous storm. The October storm, less famous. But what we see is only one Earth-directed CME. And actually the effects, if you just look at the aurora, if you take out the fact that it was less famous in the media, the reports of the aurora were very similar between the 2 storms. Excuse me. But in October, we only have the 1 CME coming out to the Earth. So here, again, we're looking at coronagraph. We blocked out the sun. We're looking at the solar wind coming out. And the 3 panels show a progression in time of the same CME. So just coming out is a bit further and even a bit further there. So it was a powerful CME, but it's less complex. So when we looked at the active region on the sun, which is the region that these CMEs are coming from, and compare the 2 events, depending on how you classify the active region, some classifications consider them equally complex, and some of them considers the May storm more complex. So it's kind of, while we have the 5 CMEs versus 1 CME, it's not immediately obvious just from these 2, just from this one analysis of the sun. It doesn't give us the whole picture. So we trace this all the way down to the ground, to the Earth, and to see, how do the storms compare? They have very different drivers, but how do they compare in terms of their effects? So again, going back to sort of the science here, the solar wind is constantly buffeting the magnetosphere. And in fact, the pressure of the solar winds, this is dynamic pressure. If you can imagine when you blow a fan into your face, if it was really fast, it would like wobble the skin in your face, like if you're on a roller coaster. That's kind of a similar thing. But if you can imagine and this is just showing the water going around the rock, by the way, is that the Earth's magnetic field is an obstacle. So the solar wind's going around, it's not going through. So when we have the big puff of solar wind coming out the sun, the coronal mass ejection, it's really punching the magnetic field in the face. And it's tons of energy, loads of energy being transferred over into the Earth's magnetic field environment. And there's a variety of different processes. I mean, somebody mentioned substorms earlier already, so I'm not going to go into all the detail of all the different ways we can generate the aurora, but lots of different things will happen within the magnetosphere as a result of that punch in the face, which will contribute to the aurora happening. So yeah, like I said, we studied the two different storms. They're different in terms of the drivers coming out of the sun, but how can we see, did those different drivers make different effects on the ground? This is an important question for space weather research because we need to understand when we see what's coming out of the sun, what's going to happen at the Earth. So this little video is going to show it's you may have seen this before. The solar winds coming out of the sun here. As you can see, this is an animation, and it's going to travel through the solar system and reach the Earth. So here's the Earth's magnetic field. You can see it punches the day side. There we go. The magnetic field lines start cycling around in the magnetosphere. And what you can see, this is one of the many processes that affect the aurora. These magnetic field lines are going to come together and then ping like a slingshot, like if you imagine pulling back an elastic band and letting go, that little cloud of particles rain down the magnetic field lines here and crashed into the atmosphere. And that's one of the many things that will contribute to the aurora. So I may be preaching to the choir here to use the metaphor in that this is the Aurorasaurus network, so I'm hoping you all know the word aurora. But just to make sure we're looking at charged particles buffeting the Earth's atmosphere. The particles undergo the one-on-one collisions. They give over their energy to the atmospheric neutrals, and the neutrals can't hold on to the energy. They shine it out as visible light. And then here we have a gift from space. So there's loads of fine structure. This is one of the things that citizen science images are fantastic for because it gives you really high resolution, high spatial resolution detection of the aurora. Yeah, and it's predominantly green, but we also see the other colors, particularly when we have these geomagnetic storms. So moving back on to the science. So I just wanted to remind you where Ireland is in case, just in case, well, I suppose it's not Friday afternoon for you, it's Friday afternoon for me. So just to make sure we're all on the same page, this is Europe, here's Ireland. I live about here, this near to this purple square of Dublin. So while space weather is driven globally, it's a really global phenomenon. That's all the previous things we've looked at have been global. In terms of preparing for the hazard, we have to be very local because the effects of space weather depend not only on your infrastructure, your electricity grid infrastructure, for example, your rail grid infrastructure, but also the underlying geology of where you are. So some geology is more conductive than other geology, essentially. So we look at modeling it specifically for Ireland. So it's in some ways it's somewhat easier because we sort of got the ocean around us, so we have the clear edge of where it matters. But in other ways it's easier because we don't have a lot of data. So very few places will share their data for their electricity grids because of security risks and things like that. I think New Zealand is one place that does that. But here we are using some space weather observations to model what we think happened over Ireland. So here we have a map of Ireland. So top row is for the May storm, bottom row is for the October storm. The left-hand column is geoelectric fields, and the right-hand column is geomagnetically induced currents. So it's kind of complicated to go through in this talk. There's so many different things on these plots, but what we're seeing in the color here, yellow is higher geoelectric fields, and then the blue or the bottom of the color block is lower. So if you compare May and October, we do in general see about 50% larger peak geoelectric field in May than October. So that complex event coming across off the sun gave us a higher geoelectric field. And it's also centered around this region here. And then when we look at geomagnetically induced currents, and these are the big risks to our technology, if anything is going to overload a power line, it's going to be this. We see, so here we have, if you focus on this red circle here and this red circle, those are the peaks, the highest GICs over these, each of these maps. It's a much bigger circle in this plot here, which said it's a bigger GIC. And it was actually one of the biggest GICs over several decades of this model. So again, the Maystorm is driving something stronger on the ground, certainly in Ireland, than in the October storm. But what's interesting about this map, and perhaps not surprising if you know a bit about Ireland, is down here in this corner, we have our largest power generation facility of the entire island of Ireland. So not only is there the power generation facility, but there's also lots of conductive infrastructure, so big, thick conductive cables going every which way to take it around the island. So not only is this our the location that's under most risk, but the reason it's under most risk is because it suffers the most with the GICs, essentially. So a lot of underlying resistive structures, how we say it in the science speak in the paper here. So that's kind of our models, but moving on to sort of what we saw from the ground, I'm just looking at the clock here. Again, we have a map of Ireland here. The purple star is the location of all these limit images. The yellow crosses are showing us where we had active magnetometers at that time. So Ireland north-south is only about 4 degrees in latitude. So while 2 magnetometers doesn't look like tons, they're only about 2 degrees apart. So that's actually pretty good. I'm not showing the magnetometer data here. I have something different in the top and bottom. This shows you the progression of the storm, and the vertical lines are showing you when the images were taken. But here, looking at the May storm, we have these 2 images here. These are by one of my colleagues here at DIAS, and you can see a variety of different colors and brightnesses. Now she's maybe looking in different directions in these 2. And then again, looking at the October storm, it seems to be a little bit less bright. Now, these are only 2 images either side, so we can't draw tons of conclusions. But you can see here we have the purple aurora and not so much here, only red and green. So sort of moving on from this study, we were kind of inspired by some papers that we saw, and obviously Aurorasaurus as well, to try and collect some images from the public. So I don't have them in the presentation because I know that you wanted the presentation recorded and they're not published yet. And we have very strict, we're trying to be very precise about how we process the images and make sure that they're not, that they're in line with data processing guidelines and things like that. So we asked the public to submit their images from the May and October storms. We collected 510 images. And along with some licensing agreements, once they're all processed, we'll be able to publish them online on Zenodo for anybody to look at and anybody to use for science. What's really fun and exciting are these kind of really beautiful images of multiple colors, or like this is almost a corona aurora, so it's almost an overhead aurora. We have many observations of corona aurora. And what's really fun to me about that is if I plot them all over the island of Ireland, I can trace the position of the auroral oval, approximately at least, as the progression of both the storms happened, which is really cool, will be a really cool science product. And also just looking at the different colors as well can tell you things about the science. And one final point about them is it was actually surprisingly, something that's really interesting about these storms. They were really well publicized. We're in the mobile phone era. We're also in the social media era. So everybody has a camera in their pocket and everybody was texting each other or WhatsApping or Facebooking or whatever, saying, go outside, go look at the aurora. So that means we were able to collect many snaps from many people in different locations. And also it became or has become a bit of a record of sort of the socio-historic impact of the storms. So we have a free text box, and sometimes people have said quite poignant things about, going out to watch the aurora with a late relative. There's things like that, and also kind of a map of the architecture of Ireland in a way. The things that are in the way of the aurora are very specific to our landscape and our, in terms of our hills and valleys and seaside, our trees, architecture specific to our locality. So it becomes also kind of as well as the space science impact, it becomes kind of a historical record for the storms, which I think is really exciting as well. So that will be submitted before the end of the year, that paper. I can't show you the images yet, unfortunately, um, but it's hopefully will be a really exciting result. So I'm just going to finish here with these images. And I'm happy to answer any questions anybody has. You can follow our social media here. You will find a huge volume of content about the solar eclipse. We had a fabulous week in Dublin. It was clear for all but like, I mean, maybe 20 minutes after the maximum, a few clouds started appearing, but they didn't cover up the sun. So we had fantastic images. We had some colleagues went on a Defense Forces plane across the ocean into the path of totality to see the eclipse. Um, so it's been a really busy week here. But yeah, I'm happy to take any questions that you have at this point. Also, I realize I think we might not be on X or Twitter anymore, but definitely on Instagram here. Yeah.
Thank you so much, Alexandra. That's amazing.